Kayraklıoğlu from the Chapel team. The two teams work very closely together. We're excited to tell you about the Arkouda project and the progress that we've made in the last year, what we're working on next, and how you can contribute if you're interested. Arkouda focuses mainly on the intersection between the productivity of Python and the high performance computing of Chapel. And so we'll talk a lot about that intersection today. So we'll go over a number of different things that we worked on this year. Each of these could have a presentation on their own, honestly. So we'll just very much touch the surface on these. And there are even some topics that we had to cut because of time. So, but we'll do our best to go through it. So Arkouda is basically NumPy for supercomputers. It's an open source project that focuses on exploratory data analysis at scale. And we use a NumPy-like syntax paired with Chapel's distributed performance. And it's basically so that people can operate interactively from Python without needing to know parallel programming or MPI or how to parallelize a loop. But they can still handle billions of elements across nodes in a reproducible fashion. And our strategy for achieving that is we try to be familiar. So we stick to the NumPy, Pandas, and SciPy semantics. So that'll make it very easy for users who are used to using those to use our tool. We also have an emphasis on scalability. So parallel computation over massive arrays. We want to make sure we're preserving performance in our product. We want to have reproducibility so people can run their experiments. And we want it to be extensible so people can add new Chapel functions easily via our message framework. And we're trying to make it accessible. To be honest, this is something that we're working on, but we're working on having an installable SPAC package and some Docker and Kubernetes support. And it's constantly evolving, so we're constantly adding new features. Right now, we have a lot of NumPy coverage, a moderate amount of Pandas coverage, and SciPy is very fledgling, but that's a growth area for the future. So the bottom line is we're trying to empower researchers so that they can move seamlessly from the prototypes that they're already writing in Python and easily just scale it up to terabytes interactively without having to worry about low-level boilerplate code.
All right, so continuing on Amanda's great introduction, I want to motivate Arkouda more by just talking about some relatively recent use cases. So my team is at HP, and we are working on Arkouda, and HP produces supercomputers, so we have a lot of telemetry data from those supercomputers, and understanding and developing future generation of supercomputers is really important. And a part of it is just understanding current supercomputers by just looking at their telemetry. So one of the things that we are exploring with Arkouda is just whether it can be used for analyzing large-scale server telemetry data. One of the use cases under that umbrella is understanding energy capping for GPUs. That is basically turning down GPUs a little bit by sacrificing their performance a little bit again to save some essentially power, and the general impact of that to users and understanding the trade-off and the benefits and the negatives of it. So this is a collaboration between HP and Oak Ridge using some data from Frontier, that is the second fastest supercomputer in the world. So this particular experiment is based off of a script that is written completely in Pandas, and we transliterated that to Arkouda. As Amanda was talking about, Arkouda has Pandas-like interface, among other things. And with that translation, we just achieved 3.5x better performance on a single node, on a single computer using Arkouda, because under the hood, Arkouda uses Chapel, which is parallel. What's beyond is Chapel also supports distributed memory programming, and you can take the same Arkouda script and put it on multiple nodes and have it scale. So on the plot that is on the right-hand side is showing weak scaling, meaning we are adding more nodes, and as we add more nodes, we are adding more data as well. So we see that up to 16 nodes, at least for this experiment, we are getting relatively flat weak scaling. That means you can add more nodes and more data to it, and it will just keep scaling. What's important to note here is pandas, standard pandas is not suitable or cannot be run on multiple nodes, but Arkouda can. Another use case again on telemetry is about understanding the relationship between environment and node failures. So for example, temperature, how does the room temperature impact node health? So imagine you have very large server telemetry data and information on failures. Can you find the correlation between the fluctuations in the environment and the fluctuations in server health? This is a larger experiment. It uses 4 terabytes of data, all stored in Parquet files. We'll talk about Parquet in a couple more slides, but it's basically a tabular data format. So what we do with this 4 terabytes of data is just we load and we do some data analytics, commonplace operations like histogram, min, max, and covariance. And this is an experiment that was run on 64 nodes of HP Cray EX, that's top of the line supercomputer from HP. And in this experiment, we compare Arkouda to Dask and Spark, or more specifically PySpark, the Python interface. Both Dask and Spark can also run on multiple nodes. And in this experiment, we see that Arkouda beats Dask by 1.7x and Spark by 4x. This is, again, Arkouda coming from Chapel background, which is designed for scalability and parallelism, and then putting the Python interface for on top of it for familiarity and ease of use, as Amanda mentioned. While talking about Python and familiar interface, I believe next up will be NumPy alignment of Arkouda, and I'm going to hand it back to Amanda for that. Amanda?
Thanks again. So next we'll talk about the NumPy alignment. This is a very important topic for our project. NumPy is the foundation for everything because pandas and SciPy depend on it. So we need to really have tight alignment for NumPy in order to align well with pandas and SciPy as well. So we mirror the NumPy API. Our goal is that a user could import AK NumPy as NumPy and use the exact same in syntax and get the same results that they would in NumPy, except that the data would be distributed on the server. We follow the NumPy docs, so we match those as closely as can. We've reorganized our code into NumPy, Pandas, and SciPy modules so that it's clear what is being aligned to which library. And we're pursuing this in 2 different ways. One is we're working on adding all the functions that NumPy has, and we are prioritizing by real world usage, by what's used most frequently by pandas and SciPy. And we're approaching a milestone where we have all the top most used functions by pandas. The other phase of that we're heading into next is to actually verify per function the parity. So really audit the code so that we have the correct promotion, broadcasting, and other features exactly match NumPy. So this chart shows our coverage of NumPy functions compared with pandas and SciPy. Pandas is in blue, which is what we're focused on right now. We have 85% coverage of NumPy functions that are used by pandas, and we have 99.8% by call volume and 99.8% by the pandas functions that touch those functions. So basically, we have the most of the heavy hitters done at this point, and what's left is that long tail of more or less frequently used functions to work on. So this chart just shows that tail, and we do use it for prioritization. So next is all closed, which is used only about 11 times by pandas, and we're actually have someone working on that right now. Because we're starting to have really good coverage on NumPy, it's a good time for us to shift focus onto pandas. And so what having that great coverage allows us to do was to implement the pandas extension array API. So we do have an experimental version implemented in Arkouda right now. It's an API provided by pandas to wrap our arrays so that we can put Arkouda arrays directly into pandas objects, such as series or data frame. And it supports 0 copy construction, which means we keep the data on the server whenever possible. And the reasons why we want to do that is to enable scalable workflows for our users. We want them to have as many pandas features as available as possible, as quickly as possible. And we want to avoid having to rewrite all of pandas because it's a very large library. So what works today are basic features. So if you register our data types with pandas, then you can use the pandas array function to directly instantiate an Arkouda array, put them directly into a data frame, and then you can directly call a pandas function such as merge in the example on the right-hand side, and it will correctly compute the answer, and it will even provide that answer where the arrays are still distributed on the server. But just heads up, it's still experimental. We're still working on it, but hopefully in the near future, it will be built out. Next slide, please. The one piece that we're missing, but we're planning on working on soon, is the bridge piece between pandas and Arkouda. So once we have that data in those pandas objects, we'll be depending on the pandas internals. And the problem is that they're making lots of choices that may not scale well or may not be performant, whereas we already have functions written that do distribute on the server. And so we want to make sure we have a way that we can choose our code over pandas codes. So the example on the right shows what it would look like for us to implement the pandas accessor, which is a wrapper that pandas allows to add functions to their objects. So in this case, it shows the merge from the previous slide, what it would look like if it was done using the pandas APR or if it was using an accessor, an Arkouda accessor. And you can see that it would look very similar to the user. It would give the same answer, but it would give us the opportunity to call the Arkouda logic in the background, which would scale better. So again, this is experimental. We have the arrays and D types implemented on a very basic level, and the bridge layer is still in the future. All right, we've also spent a lot of time building up the random module in the last year. We use the Chapel's PCG64 backend. We've added most of the basic, most commonly used distributions like normal, standard, normal, exponential, Poisson. Utility functions like choice, permutation, shuffle. We have some method variants that you can choose, and we also try to respect the legacy API, so it'll be backward compatible. We also have a global seed, and they are deterministic. The results should be stable if you have the locale count unchanged. One problem that we have currently is there is some locale sensitivity, so that if you change the number of locales, then it may not be reproducible across that change. But we do have one recent advance, which is locale invariant exception, where we have a Feisel method added to shuffle. But the Feisel algorithm, it allows us, it's a stateless permutation. So it allows us to pre-compute a bijection that we can use for the shuffle that allows it to be locale invariant. And so going forward, we would like to add that locale invariance to the rest of our random module. And it basically comes down to the observation that most data science applications don't really need cryptographic security. We just need to have a really strong randomness and reproducibility. And so that gives opportunities to explore other methods like stateless RNGs that are used in other machine learning projects. So I'm optimistic that we will be able to achieve this in the near future. And another big addition in the last year was multidimensional arrays. So we now have almost full multidimensional array support for all of our numeric arrays. So you can create them, you can reshape them, broadcasting aligns with NumPy, all the numerical operations should work, manipulation functions, most of the reduction functions. We do have some, just a small number of linear algebra functions and some sorting algorithms that work with multidimensional arrays currently. And so for what we have left in the multidimensional arrays, most of them are just small to-dos that will be done shortly. The two notable ones that will be longer till we get to are the strings. We store strings in a special format that will take a little bit more work to implement in a multidimensional case. And pandas integration, right now we only support one-dimensional arrays. Multidimensional arrays are on our radar, and we plan to get to that eventually. And now I'll hand it to Engin. He'll talk about Parquet IO support.
Thanks, Amanda. All right, so I'm going to talk about some optimization that we worked on Arkouda server about Parquet IO. So if you're not familiar with Parquet, as I mentioned before, it's a columnar or tabular data format. And for this toy example, let's just assume that we have this logical table where we have 3 columns and a bunch of rows. So Arkouda can read these kind of tables that are represented in Parquet files, and what it would look like is on the client, there is a data frame just like pandas, but this data frame just has PD arrays that are on the server side for each column. So one interesting observation here is that the Arkouda server does not know about data frame. It just knows about columns individually as independent arrays. And the client is the entity that stitches them together and represents them as data frames. So this is basic Parquet, very quick Parquet format introduction and how it's implemented in Arkouda. So if you look at a sample Parquet file, it actually looks like this. So it's a columnar format, meaning the data belonging a column or each column is together, typically in a file, but it does not necessarily mean columns are always together from start to finish. Specifically, if the file is large enough, and that's just a couple of hundreds of megabytes, it doesn't have to be like exascale file or anything like that. Parquet files are stored in what's called row groups. So for example, if you look at column 0, it's not stored all together, but rather it's striped across multiple row groups. So Arkouda's Parquet implementation previously was just reading files column by column because it's a columnar format and it fits well with the server's representation of data where each column is a separate PD array. So it just gives you the opportunity to just fill one array and the next array and the next array on the server side. But if you account for the representation of the file, especially if the file is large enough, what this would look like is to read column 0, we would be just jumping around the file to read everything from column 0. And on the right-hand side, on the server side, we are just filling the first array. And when we are done with the first array, we just jump back to the beginning of the file to fill the second array. Now, if you just look at the server side of things, this makes sense. We are just filling arrays one by one, but at the same time, your IO is kind of unnatural in the sense that you are reading the file almost again and again and skipping bunch of the bytes stored in it, if you will. And considering the fact that IO is typically much slower than memory, it's really important for us to do things in a more sort of IO native or IO natural way. And what we worked on in the last year, well, particularly actually in the last couple of months, is to change Arkouda's Parquet reads in a more natural way. So now Parquet files, particularly if you're reading all the columns, which is the common case, we just read the file linearly without jumping back and forth, and we try to fill arrays, multiple arrays on the server side that represents columns at the same time. I'm sorry, my arrows look a little bit off there, but you understand the idea that we just fill in chunks of multiple PD arrays instead of just filling one array in full. So in synthetic benchmarks, this shows really great improvements. So this is a first case of a synthetic benchmark that we run with, 400 gigabytes of data spread across 5 columns. We got 1.8, 1.78x improvement. And if you take things to the extreme where you have 1,000 columns, as in this synthetic benchmark, I don't know how realistic that is, but I'm sure there are some Parquet files out there that has more than 5 columns too. So you can think of these 2 data points as 2 ends of the extreme. With 1,000 columns, we are exceeding more than 33x performance improvement with this change. And this improvement actually was motivated by one of the use cases that I mentioned about in the introduction, where we were reading terabytes of Parquet files. And now, thanks to this change at scale, we have achieved more than 2x improvement for that particular use case. And on the right-hand side, you are seeing the weak scaling of that use case where we actually achieve better behavior, where the flatter you get in weak scaling plot is better. Now, obviously, we are not perfectly flat. We have some ideas as to how to make it flatter, but with this change going from blue to orange on the right-hand side, you are seeing that we are getting close to flat behavior on weak scaling. Next up is sparse computations. In basically our march of improvements over the last year, or that's why we called it Bulletin, I guess. It's just a bunch of different news. So sparse computations is another area where we did a lot of performance improvements. So when we first started, the challenge here was to create a distributed sparse domain array pair on Chapel side on the server using 3 Arkouda PD arrays that represents row, columns, and values of the sparse matrix. And these Arkouda arrays are not necessarily sorted. The data in them are not necessarily unique. So it could be just completely random data that we need to handle. Well, the potential answer for that, of course, you can do that in Chapel. If you have just arrays of indices, you can just do plus equals on a sparse domain in Chapel, and the indices will be added to the sparse domains, and easy peasy. Then the next challenge is, can you make it run fast at scale? And that's a more challenging challenge, if you will. So the answer is not very clear. For that, what we come close to in Chapel before our effort is called copy aggregation. So let me do a quick background on what copy aggregation is. So it's a very common operation in data science or in other fields to copy random data or randomly ordered data into an ordered array. So you're just touching memory in a random fashion and just storing everything in a nice orderly fashion. In fact, this for all loop does that in parallel. So if I can walk you through this 2-line loop, I'm just zippering over 2 arrays, assume that both are distributed. So I have my destination array. An element of that is DST. I'm sorry, loop body says D, but it should be DST. What I'm doing is I'm copying from source array and an index, and that index is coming from another array called source indices. That is something that I'm also zippering. So this is basically random access on source array. You can do this, and it would work just fine. You'll get correct results. That's fine, perfectly legal Chapel code, but it will not scale. Because every time you touch source array, there is a good chance that it's going to be a remote data, and it will induce communication for every single index. Solution in Chapel and solution that Arkouda uses heavily for its scalability is called aggregators. And this is the aggregator-based implementation of the same loop. As you can see, the changes in the code is modest, where we introduce this aggregator type as a task private variable to this for all loop. So every single task has its own aggregator. And instead of doing an assignment, we are just calling the copy method on the aggregator. What the aggregator will do under the hood is it will just buffer the data before copying it so that the data is copied in larger chunks instead of one by one. And this really helps Arkouda scale. So, maybe our answer to the challenge is to use copy aggregation. But copy aggregation, as the name kind of suggests, is just about copying the data. So you can copy the data from one array to another, but then how do you add that to a sparse domain and array? So that's why we worked on custom aggregation, a general solution for Chapel that will be used by Arkouda. So this is a slightly more complicated version of that for a loop that shows our current prototype. So with this prototype, what happens is you have this custom aggregator that takes a handler. So this handler can describe whatever arbitrary operation you want to do when the data is moved across the network. So this way, without actually having to copy the data multiple times through a local array first, you can just copy the data in an aggregated fashion and populate a sparse domain and an array on the receiving side. So this is the quick result from that experiment. The blue bar here is just showing a matrix multiplication algorithm implemented in Arkouda already. This is multi-node sparse matrix multiplication algorithm. The red and purple bars are matrix creation times for CSR and CSC representation. The difference doesn't really matter here, but what matters here is you were actually spending more time just creating matrices instead of multiplying them because of lack of aggregation. Now, with that effort, what we had achieved is 34x faster domain and array creation, or like a matrix creation. And as you can see, the creation time is minuscule compared to the actual matrix multiplication, which is the behavior that you'd like. Before I hand it back to Amanda, I'll just mention 2 other improvements as honorable mentions. They are still work in progress, but we are really excited about them. First one is checkpointing capability that we added in the last year. So now you can checkpoint Arkouda server's state. You can think of it as just saving your game and loading it back up when you want to. You can use that for that purpose. You did a lot of data analytics. You save your work, go to your vacation, come back next week, and then keep going on. Or alternatively, you are doing data analysis for 3 hours. You're afraid of, a server crash, electricity will go out or something. You just save your checkpoint and then you can load it back up again to save you some time. And you can also enable checkpointing automatically if you reach some memory threshold or if the server is idle for some duration. But this automatic checkpointing is not on by default. Last but not least, the honorable mention is Python interoperability on Arkouda side. If you're following developments on the Chapel side, we have this new Python module where you can just call arbitrary Python function, and that's exposed to Arkouda using the apply function, where you can just pass, for example, a Python lambda to ak.apply, and it would apply that Python lambda onto the PD array that is actually stored on the server. And that gives you ability to do any arbitrary Python operation on Arkouda arrays, which can be distributed. And with that, I think I'm going to hand it back to Amanda. Amanda?
Well, thank you. So Outlook, what's next? We're going to complete the per function alignment with NumPy semantics. We're going to continue to deepen our Pandas support and data frame operations. And we have a lot of other things that we didn't have time to mention. We're working on improving our benchmarking, diagnostics, tools for developers to make it easier to contribute. We are an open source community. We have 13 active contributors over the last year. We would love to have more. If you want to visit our GitHub page, we would really appreciate that. You can check out our code, make some code contributions, add to the docs, testing, new use cases, even to make bug tickets and feature requests really helps our team. So we really appreciate that. Thank you. And in conclusion, in 2025, it's a more mature NumPy-like framework for distributed analytics. We have stronger alignment with NumPy 2.0. We're increasing our Pandas alignment. We've added a lot of features, multidimensional Python interop, random utilities, sparse matrices, and checkpointing. We have faster Parquet IO now, and we're continuing to try to improve our packaging with SPAC and Docker. So in short, we bring Python's productivity to HPC so that data scientists can do reproducible computation at interactive speed. Thank you for attending our talk, and thank you for everyone who contributed in the last year.
Thank you both so much. And plenty of applause from the crowd. I don't even have to ask for it. Does anyone have any questions? I'm sure folks are furiously typing their questions into chat. And Lydia, go ahead. Thanks.
If there was one feature that you wanted to add to Arkouda with the snap of your fingers that maybe has been put off due to like effort or something like that, is there anything that you would add like that?
For me, well, I would really like to get Pandas completed. And one thing that I was excited about in the last year was the apply function that was added. We've gotten numerous user requests in the past to have a apply function. So we're excited. I'm excited that we have the capability now. We still need to build out the Python side of it to get it working more completely with Pandas.
And I have a question about checkpointing. Namely, like just like what does it look like time-wise to sort of restart from a checkpoint currently?
Yeah, that's a good question. So what we do with checkpointing is basically just writing a bunch of Parquet files. Parquet has been our key I/O feature, as you could have guessed from the presentation. So whatever Parquet performance is the short answer. And kind of a longer answer is that's one of the reasons why we are working on Parquet IO performance, because it can make checkpointing itself faster as well to load the data size, to load the data essentially. So there's no clear answer to your question, but it's basically however long it takes for Parquet writes and reads for happen. Oh, I broke that sentence, but you understand what I mean, right? Like it's dependent on the Parquet IO performance, and I believe you're at a good point in Parquet IO performance.
Awesome, thanks. And let's take this last question from Brett. We'll have this be the last question, and then Luca has a question in chat, but let's go with Brett's live question here.
Hey, yeah, thanks. More just a comment. I was just I haven't worked with Arkouda for about a year, but I used to work with it, and I was just happy to see with the SPAC improvement, for easier deployment, and then also the checkpointing. Um, when I worked with it, I was always like when I was trying to run it on Frontier, I always had issues with, wanting checkpointing and just that whole process of using it on or of doing stuff on Frontier, and that looks like good progress in the past year. So thanks.